Hey everybody, it's Mr. Carr again. Today we're going to be looking at 3.2 day 2, applying what's called the fundamental theorem of algebra. So polynomials, we've talked about their graphs, a little bit about their end behaviors and everything. But now we're going to talk a little bit more about that and what's called the fundamental theorem of algebra. So a polynomial of degree n has exactly n solutions. So what that means is if I have a degree of like x to the second power, there's going to be two solutions. We've seen this before. This is a quadratic, but here's the thing. You can have two solutions in a variety of ways. You can have two real solutions. You can have one real solution, but that happens twice in a way, if you remember what we did with that one. And we could also have two imaginary solutions. So this, like I said, we're going to count twice, triple solutions. Okay, these are all part of it as well. So how many total solutions do we have in both of these cases for these polynomials? It is just straight up about this right here. The highest degree is 3. So that means there's going to be, 3 solutions. Okay. For this next one, 6 is there. So I'm going to have 6 solutions. Okay. This is a quick aside that's like an extension off that. When I have something like this, we have an odd number, we can have 3 solutions. So that means we can have 3 real solutions, or we can have one real solution. Well, we could actually have 2 real solutions as well, but we could also have one real solution with 2 imaginary solutions. You're always, if you ever have imaginary solutions, they have to exist in pairs. So you cannot have like 3 imaginary. It's got to be 2 imaginary or 4 imaginary and so on. Okay. So because we know, come here, because we know that the x-intercepts of a graph represent the real zeros, we can combine this with the fundamental theorem to find our number of imaginary zeros. So find the number of total zeros, real and imaginary, of this polynomial. So first off, I'm going to do all 3 of them. Our total is, again, based on the highest exponent. So there's a total of 4, a total of 5, and a total of 6 here. But let's go to the graphs to see what they look like in terms of actually crossing the x-axis. So when I come here, here's my first one. Don't worry about all the extra ones for now. We'll get to those in a bit. Okay. So here's x to the 4th minus 6x squared minus 4. You can see it's crossing 4 times. So I have 4 real solutions. So if I come back here, there are 4 real and 0 imaginary. Let's look at x to the 5th minus 2x plus 1 there. So we turn this one off and we'll look at this one. Here I'm crossing 3 times. Okay, I'm crossing 3 times, but according to our chart here, there's supposed to be 5 total zeros. So there are 3 real ones, meaning there has to be 2 imaginary here. For my last one, we got x to the 6th plus 3. So we'll go to that one, x to the 6th plus 3. That never crosses. And it does this curve here where it comes in, flattens out a bit, and then comes back up. So what that means is it's never crossing. There are 0 real solutions. So if there are 0 real, then that means there has to be 6 imaginary. And like I said earlier, you notice how the imaginary, there's 2 and then there's 6. They have to be even number of imaginary no matter what. So here's a 4th degree polynomial. So as we'll learn about soon, imaginary zeros come in pairs. Okay, so let's take a look at this one. If this is 4th degree, we see that it's crossing 1, 2, 3 times. We know it's 4 total zeros, but we only see 3 real. So that would almost make us seem like, hey, there should be an imaginary one there, but imaginary can only exist in pairs. So there should be 0 here. So why is there why is the number off? It's because of this one right here. Whenever a polynomial bounces on the x-axis, it represents a double solution, or it could be quadruple. And I don't want to come up with the words for the ones. Or, so it's, okay, sorry. It represents a double solution. So it happens 2 times. But the solution could also happen 4 times or 6 times or anything else that's an even number of times. Okay. So that's what we're looking at here. Okay. So what we're looking at is this bounce. The graph is coming across, it comes here, it hits the x-axis and bounces away and then comes and hits again. Okay, has its own term, which maybe we'll go over in the future, but not right now. So that's why we have these, like the numbers are off. That's why we have 4 total, but only 3 real, because one of them, one solution is happening twice. One solution is twice. We'll write it that way instead. All right. So graphing the function on graphing calculator. Let's look at what the next idea, which is turning points. Okay. So turning points, if I come back here a little bit, is referring to this. The graph is going down, it turns and starts coming back up. Then this is another turning point. It goes up and then comes back down. And then this is a third turning point. Okay. So we're looking at that idea. So our turning points in this case. So let's look at each of these cases here. We have x cubed, x to the fourth, and then x to the fifth. So I'm just going to go all 3 of them real quick. So we have these 3 right here. So here's this one. You can see on the graph. There we go. Here's 1 and then 2 turning points. Okay. Here's that second one there. If I do this one. Comes in, here's 1 turning point, 2 turning points, and 3 turning points. Okay. And then we look at this one. Zoom out a little bit here. So we go 1, 2, 3, 4, 4 turning points. So what we're seeing here is, there we go. The number of turning points is 2. The number of turning points here was 3. And the number of turning points here is 4. So what does that mean? To me, when I see that, I'm going to say that, hey, 3 is 1 less than 4. 2 is 1 less than 3. 4 is 1 less than 5. So if I look at this one now, I would expect 2 turning points. So let's take a look at that. So if I take that one, we're close. There's this weird little thing here. Okay. So that's x cubed minus 2x1 does not actually have that. So it didn't work this case, but that's okay. We took a guess on that one. But there is a concept behind that. We can have, if I can make adjustments to this one, I don't remember if I can, what it would take. Let's try, there we go. If I made that a 4, now I have 2 turning points. So here's the thing. With this, we have the polynomial of degree n has at most n minus 1 turning points. Okay, so we have the same number of, whatever the degree is, that's the same number of solutions, but the turning points is always going to be 1 less at the most. We have these other scenarios where it's not going to be a turning point, like that previous example there, that actually has what's called an inflection point, but we don't have to worry about that right now. Let's do another characteristic here. Local maxes and local mins. These are our turning points. Okay, a local max and local min is kind of like when we talked about maximums and minimums in the past. It's a highest point or it's a lowest point. So if we have a local max, we have something like this right here. A local min, same kind of curve, would be the bottom of that one. But it's not the absolute maximum or absolute minimum. They're just little turning points ideas. So let's use our graphing ability to find those points. So we'll do this one next. That's going to be right here. So with a graphing calculator, TI-84 or Desmos, you're looking for these points. Okay, and that's what we want right there. I like Desmos for this because we just click on the graph and we find them. If you're doing this in TI-84, you have to go through the second trace and work through all those. So for my purposes here, let's see here. Just got to write that down for myself. So let's go back and we'll just draw a rough sketch of this graph. Okay, we had a local max was at negative 1.87 and then 5.06. And a local minimum of 0.54, negative 1.88. Okay, so if I graph those out, I just do a very rough sketch of that. It's like right about here-ish, negative 1.87, 5.06. And then 0.54 is going to be down here, we'll say, something like that. 0.54, negative 1.88. So my graph looked just something like this. Came here, here, and like that. Okay. Again, local mins and local maxes are referring to these 2 points. So our last idea with this thing. Let's do a full analysis of our polynomial. Okay. So we have x to the fourth minus 6x cubed plus 3x squared plus 10x minus 3. Here's a couple things that I can do. Before I go to the actual graph and get everything on here, I'm going to analyze all these ideas here. So it's a fourth degree. Leading coefficient is a positive 1. So that means I can look at my end behavior. A sketch of that would look like this. Even degree with positive coefficient is going to both go up. Now, how I write that, remember the formal way to write that is as x approaches infinity, f of x approaches infinity. And then as x approaches a negative infinity, f of x approaches a positive infinity as well. Okay. I know the total number of zeros needs to be 4, but now we're going to have to graph it in order to get our real zeros and imaginary zeros. So let's go to the graph now. But I can just get a feel for what this looks like. I know that it needs to be, something that's going to end up in the up here. Potentially with 4s, it could go 1, 2, 3, 4. Okay, so I could have 3 turning points like this. Okay. Bottom line is we got to go to the graphing calculator for now to find this. So from here, and we do get our, 3 turning points way down there. Zoom out a lot on that one. Okay. So we get 4 real zeros. Yeah. That one too. Okay. So we got 1, 2, 3, and 4. So there's all 4 of them right there. We're going to put those on our answer sheet as well. Our local minimums, we have 2 of them. We got this one here at the bottom of that little hill or valley, and this one all the way down there. We also have a local max right there. Okay, so I'm going to go ahead and plot those. Okay, I'm going to write those all down for myself and then also plot them very roughly. So we had 4 real zeros and 0 imaginary ones. The 4 real zeros were negative 1.14 comma 0, 0.28 comma 0, 1.82 comma 0, and 5.03 comma 0. The maximum, we only had one of those. That was 1.11 and then 5.11. Our minimums were at negative 0.57, negative 6.51. And then the other minimum was 3.96, negative 43.04. Ooh, okay. So I can plot these, roughly. This is going to be way off the graph, but I can do the other ones pretty well. Negative 1.14 is going to cross about there. 0.28, about right there. 1.82, close to there. And then 5, 1, 2, 3, 4, 5, basically right there. Maximums was at 1.11, 5, 1, 2, 3, 4, 5. Roughly there. And then we have minimum negative 0.57, and then 1, 2, 3, 4, 5, 6 and a half. 2, 3, 4, 5, 6 and a half right there. And the other one's way down here off the graph. So again, we have those points. I can draw a curve that kind of connects them, follows that behavior. So it goes here, it bounces up, then it bounces down, comes way down here, then whatever. Yeah. Unfortunately, there. Let's get rid of that little part there. Yeah. Okay. So, and that's it. That's what we're going to find for our zeros for now. So again, we're just doing our graphing to find these parts. If you're going to do this in TI-84, you're going to use the different button presses, but you can still get everything that we just got here. You're just going to find the zeros using the graph feature of that one, the second trace button. then you're going to find the maximum using the maximum feature. And then you can find both local minimums by doing that as well. Okay. And that is it for today. Again, we got a lot of things going on here, but our fundamental theorem of algebra is that the degree determines how many zeros we have. We can have up to the same number of real zeros, but we might have a combination of double or triple solutions as well as imaginary solutions. Then we can also look at our other behaviors as well, like with local minimums and local maximums. All right. That's it for today. Take care, everyone. Oops, not quite.